Okay, now let's start with DC circuits. We have two types of sources of electricity. One of these is the direct current. We have a battery. The battery will give us a constant current, that the current have a constant value in magnitude and direction. Okay, the current all the time moves in one direction, which is the conventional current. We use it all the time. In power supply, you may have a direct current or alternative current. Most of the power supplies give us a direct current, okay? An alternative current, sorry. An alternative current, the current change its magnitude and direction, okay? And by a high frequency. Frequency in houses reach about 50 hertz. That means the current will move in both directions. Once the current moves anti-clockwise, and then it's back to clockwise, and its value from 0 to maximum, back to 0, back to negative value of the maximum, and so on. So this is the alternative current. The electrical circuit, it consists of many parts, okay, starting from battery, and we have a wires and some other parts. This is the symbols of the circuit component. We have here a cell. The smaller one is negative and this is the positive. Maybe we have a battery which is consists of many cells. This is the switch. This is an open switch. In this way it's closed. This is the symbol of earth. It is just 3 lines or 4 lines. This is the relay. We use relay to allow a small current can make a huge voltage to pass through the other circuit, okay? It's work as electromagnetic switch. This is the lamp, and this is a fixed resistor. If we add arrow like this, so we have a variable resistor. LDR, light dependent resistor, it's made from semiconductor material. These symbols like sun or light. Here a thermistor. We have a diode. Diode allows the current to pass in one direction. So this is the diode. It will rectify the current, so it will change the alternative current to direct current. Capacitor, it stores energy and charge for a short time. Ammeter, which is connected in series with the circuit to measure the current. We have many types of ammeters. One of these digital and the other is electronic one. Here the ammeter, it's connected in series, and this is the lamp, so you can find the amount of current. The ammeter, if it is before or after the battery or the lamp, you will have the same value through all the circuit if there is no branch like this. If we have two bulbs connected in parallel, so the current will split in two parts, I1 and I2. The total current when it's back through this point, it will be equal to the current N, which is the total current. The voltmeter connected in parallel with the device to find the value of the potential difference if it is connected to an appliance or a bulb or whatever, and if the voltmeter connected parallel to the power supply or battery, the value is the electromotive force. We have a central zero galvanometer. Galvanometer can check very small and can measure very small currents. Galvanometer can find the value of the small currents. This is the symbol of a transformer. Transformer consists of iron core, and we have here wires and here wires. If the number of turns in the secondary coil, which is connected to a device, larger than number of turns connected to the power supply, so it is a step up transformer. So the voltage here is larger than the input voltage. Here the iron core, if we have no line inside here, so there is no iron core inside. But if we have a transformer with iron core, it's better and more efficient. This is the junction. That's when you have a circuit and there is a branch for the current here. This is the junction. Light emitting diode, it's like the diodes or lights nowadays we use. All of these are LED. These are light emitting diodes, and we have many colors of these. Now, again, what is the difference between electromotive force and potential difference? If we have power supply and a bulb, if the voltmeter connected in parallel with the bulb, so this value is the potential difference, and if we connect the voltmeter parallel to the battery, the voltmeter measures the electromotive force. Electromotive force, it is the energy converted from other forms to electrical, okay, per unit charge. Potential difference, it is the energy converted from electrical to other forms of charge. So this is from the power supply and this inside the device. Now, if we have many batteries connected in series, so the total voltage is the sum of each voltage individually. So here the total is 5 volt, okay? But if the batteries are connected in opposite direction, this 3 and 2, these are connected in opposite directions. So the total voltage is 1 volt with the larger voltage. Now, inside the battery, there is a very small internal resistance, okay? It's very small internal resistance. In O level, we didn't talk about this at all because it's very small and sometimes we can neglect it, okay? The internal resistance will take some of the energy of the battery. So not all of the energy from the power supply is going out because there is an internal resistance. It will take some of the energy, okay? Now, when a car engine is started with the headlights switched on, the headlights sometimes dim. This is because the car battery has a resistance. So the resistance inside will reduce the amount of current that can pass through. All power supplies have some resistance between their terminals called internal resistance. The term small r used for internal resistance. So the amount of electromotive force, okay, will split to some voltage is taken by the internal resistance and the other voltage will reach to the resistance outside or the load. So E equals VR plus V capital R. The electromotive force will split, okay? VR, the voltage of the outer resistor, is called the terminal potential difference. So the terminal potential difference is the potential difference between the terminals of the cell when current is being delivered. If we have no current inside the circuit, which means that the switch is turned off, okay, this is the outer resistor, this is the switch, and here we have internal resistance. We can write just small r next to battery, or we can draw small resistor here next to battery, or sometimes we can put a block like this to mention that we have an internal resistance here. If the switch is open, so we have no current. So if you put a voltmeter parallel here and the switch is open, so the value of the voltmeter equal to the EMF of the battery itself, let's say 3 volt. When you switch on the circuit and the current start to pass. So we have small value of voltage, which is equal to I multiplied by small r, which is the potential difference used by the internal resistance. This value will subtract from this. So the battery will not give you a total of 3 volts. Maybe you have 2.9 volts because 0.1 volt will be used by the battery. This value, which is V multiplied by R, is the lost volt. So the lost volt equal EMF minus the voltage of the terminal. And all the companies try to make the amount of lost volt very small to make the battery more efficient. You can feel the energy lost by touch the battery. You find it is very hot because of the energy converted from type to another. Now, the lost volt equal current multiplied by internal resistance. Warning, do not try out this experiment as the wire gets very hot. There is also a danger of the battery exploding. What is the experiment? The maximum current that the power supply can deliver will be when terminals are short circuit by a wire. That means we put a wire with a battery only of negligible resistance. The internal resistance of the wire is almost 0. So the load resistance is 0. In this case, the potential difference across the internal resistance will equal to the EMF. So may the battery getting hot or the wire getting hot, or maybe the wire is melt. Okay, what is the effect of internal resistance on power from the battery? The power delivered by a battery to a variable external load resistance can be investigated using circuit as in figure 20.4. Variable resistor, power supply, and voltmeter parallel to the load resistance. Reading of current I and the potential difference across the load are taken for different values of the variable load resistor. The product current multiplied by resistance. Okay, so we have the voltage, or if we want to find the power, it's equal to the current and the voltage across the external resistance or the load resistance. Figure 20.5 shows the variation with load resistance R of the power. We have here a load resistance, and the amount of resistance, the external one, increases from 0 till a value, maximum value. If the resistance of the variable resistor is 0, the power is 0 because there is no reading on the voltmeter, because V equals I multiplied by R. If R equals 0, so the voltage 0, and P equals IVV, the voltage is 0 and current 0, so we have no power. As the resistance increases, when the value of the load resistance equal the internal resistance of the battery, we have the maximum power. Okay, this is a very important for external exam. Okay, in paper 1 mainly, this is a famous question. Okay, when the internal resistance have the same value as the load resistance, so we have the maximum power, and as resistance increase, the power decrease. So a battery delivers a maximum power to a circuit when the load resistance of the circuit is equal to the internal resistance of the battery. Now, we have many types to connect the resistors together. Let's start by series. If we have resistors or bulbs connected in this way, so if we have here a meter and here a meter, and the current pass from here, So same current will pass through all resistors. So I1 equals I2 equals I3, which is the total current, which is the same current. Okay? But the voltage in each resistor, it's maybe the same if all resistors have the same value, or maybe the value of the voltage across the first resistor and the voltage across the second resistor and the third resistor have to be equal to the voltage of the power supply. So the voltage will split on the resistors, maybe in equal value if these resistors have the same resistance, or it's differ, okay, if the resistors are not the same. Using Ohm's law, which is V equals IR, so we have IR is equals to I1 R1 plus I2 R2 plus I3 R3. We know that the current is the same from this relation, so we can take I away from the equation. So the total resistance for the resistors connected in series, it's the total sum of the resistors itself. Okay? The amount of the total resistor in series is larger than the largest resistor, which means if we have here 2 ohm, 3 ohm, 3 ohm, the total resistance is 8 ohm, which larger than the largest resistor, which is 3, because this is a connection of series. Now, if we have resistors or bulbs like this connected in parallel, okay, in parallel, the current, when it reaches this junction, we have a split of current. So we have I1 through branch 1, I2 and I3. When the currents are back to this point or this junction, we have the main current again. So the reading of the main ammeter is larger than the reading of the other ammeters. But we know that I equals I1 plus I2 plus I3. But the reading of the voltage is the same for all the bulbs. So V equals V1 equals V2 equals V3. Now, using Ohm's law, which is V equals IR, we can use I equal V over R and put it here. V equal R equal V1 over R1 plus V2 over R2 plus V3 over R3. Okay? Now, since the voltage have the same value, so V can be deleted with the other V's. So what we have by the end, we have 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. The total resistance is smaller than the smallest resistor. How? If we have here 2 ohm, 3 ohm, 6 ohm, the total resistor must be less than 2. Okay? For a special case, if two resistors connected in parallel, instead of find the value like this, 1 over R equals 1 over R1 plus 1 over R2, and you put, let's say, here 3 ohm and here 6, we have 1 over 6 equal 1 over R. So we have 6 divided by 3, 2, 1 equals 1 over R. So 1 over R equals 3 over 6. You have to take the reciprocal of this value, which is 6 over 3, which is equal to ohm. We can calculate the resistance easily using the relation R total equals the multiplication of the resistors divided by the sum of the resistors. This is used only if we have 2 resistors. For 3 resistors, this law is not usable. Here we have an example for the circuit figure 20.9 states the readings of the ammeter 1, 2 and 3. Here we have the current. The reading of this ammeter is the same as this, okay, because it is the same branch, so the reading of I1 is 0.175. Now the current split here and here. This is 75 milliampere, okay, so you can subtract this from the main current to find the current here. Now here the current is 25 milliampere, subtract it from 75 milliampere, so the current of this ammeter is 50 milliampere. The current from this branch and this are summed together, and when they reach here, the current is the total of all of these currents. Okay, now you can see here the current is split into parts. Okay, this is what is known as Kirchhoff's first law. That's the total current pass through a branch like this. It is the sum of each current, okay? The sum of currents entering a junction in a circuit always equal to the sum of the currents leaving it. So here we have 3 ohm, and the current leaving the junction is also 3 ohm. This is happen in a parallel circuit, but if we have a series circuit, the current is the same through all the bulbs or the lamps or resistors, whatever. Okay, and Kirchhoff's law is a conservation of charge. Okay, the charge in first law of Kirchhoff is conserved. So we have a conservation of charge. Why? Because this is the main current, I1, I2, and I3. I equals I1 plus I2 plus I3. Current equals charge over time. We have the same time through over the circuit, so the total charge equal Q1 plus Q2 plus Q3. So Kirchhoff's first law is a conservation of charge. Okay, what about Kirchhoff's second law? Kirchhoff's second law, it's a conservation of energy. Remember this very well. Conservation of charge for Kirchhoff's first law, conservation of energy for Kirchhoff's second law. In Kirchhoff's second law, the sum of electromotive force equal the sum of the potential differences. The sum of electromotive force in a closed circuit is equal to the sum of potential difference. This means that this voltage equal V1 plus V2. This is Kirchhoff's second law. Here we have 2 batteries, so E1 plus E2 equals V1 plus V2. Okay. And as we said, in parallel, we can find the total resistance by taking the reciprocal of the sum of the resistors. We mentioned this before. Okay, let's try this example. Calculate the equivalent resistance of the arrangement of the resistors in figure 20.16. Here we have 2 resistors in series, so the total resistance is 6 ohm. Here again we have a total resistance of 6 ohm. Now, these are connected in parallel, so 1 over 6 plus 1 over 6 equal 2 over 6, so the total resistance equals 6 over 2, which is 3 ohm. Here we have 3 resistors, 2 of these connected in parallel, so this total we can find it using the fast relation, which is 4 multiplied by 2, which is 8, divide by 6. Okay, 8 divided by 6, and this connected in series with the next one, which is 3 ohm, so you have to add 3 here. You can find the value of current, the value of voltage, depending on Ohm's law, V equals IR, or other equation. We can find the power, so you can calculate many things through these circuits. Here in figure 20.18, calculate the effective resistance between points A and B in the network in the figure. So you can find the total resistance from A to B. You can draw this like here A, 20 ohm and 10 ohm in series, and this is B. And we have 100 ohm and 50 ohm in series also. So 20 plus 10, 30 ohms, 150, it is 150. These are connected in parallel. So 30 multiplied by 150 divided by 150 plus 30, which is 180. In this way you can find the value of total resistance between A and B. You can draw the circuit in a best way depending on the values you use. Okay? Now, using Kirchhoff law, second Kirchhoff law, you can find the total voltage through a circuit, or you can find the amount of electromotive force through a battery. We have a resistor like this and resistor like this. This is the EMF, this is the voltage of first and second resistor. We know that E equals V1 plus V2. Now, we have to remember these notes, which are for two identical resistors in parallel, the combined resistance is equal to half of the value of each other. If these are identical, which means we have 1 over 2 plus 1 over 2, it is 2 over 2, which is 1, and the reciprocal is also 1. So the amount of the total resistance is half of each of these, okay, because these are identical. For resistors in parallel, the combined resistance is always less than the value of the smallest resistance. That's all for now. See you later, inshallah. Assalamu alaikum wa rahmatullah.